challenges for the millimeter wave communication. The blockage and all these are, obstacle for the millimeter wave success. Any other question? Okay, so this is the integrated access and backhaul I mentioned. So millimeter wave frequency cannot travel very far away. It can go up to 200 meters only. So the people use, Release 16 introduced IAB, is called integrated access and backhaul. So what is that is happening is it's like a relay nodes. G node B is the base station, or IAB donor that can give wireless backhaul to IAB node. This IAB node will give you service to the users. So it can be a one hop or it can be multi-hop as well. So this is a wireless backhaul and wireless access. So that's what is called integrated access and backhaul. So this is one of the technology which is introduced in 5G. Okay, so these connections are a wireless connection. It's not a wired connection. Yeah. So and the G node B is the base station or IAB donor. This is connected to the core network. Yeah, so yeah, this there are two study items happening in the non-terrestrial, terrestrial and non-terrestrial network. One is 5G NR for non-terrestrial network, and the 5G NR, 5G IoT for non-terrestrial network as well. Yeah. Okay. So with that brief introduction, now maybe I can start about the wireless fundamental of wireless communication. If you have any question, please ask me. So next plan is to study some physical layer stuff. This is kind of good for MTech and PhD scholars. Let's start. So so wireless communication, so this is the kind of a basic stuff, okay? So wireless communication is still one of the most vibrant area in communication field, okay? This is still a very active field. So last kind of a 2 or 3 decade, there are a surge of research activities happening in wireless communication and still happening as well. There are 3 reasons this research is very active still. Because the explosive increasing demand in connectivities like telephony and data application. So because of the explosive increase in demand for connectivity, the wireless research is still very, very active. The second reason is, we have done a very, very successful research on the VLSI technology that enable us to implement a very, very sophisticated signal processing and coding techniques in a very, very small low power chips, and that can be put in your mobile device. So because of the, this silicon technology enhancement lead to very, very complex signal processing and coding techniques. For example, coding techniques like LDPC code, low density parity check code. This code was invented in 1960s, but until 1990, this coding cannot be implemented feasibly because the complexity is so high. So because the silicon technology enhancement enable us to implement this sophisticated signal processing and coding techniques in a very, very low power chip. So because of that, people are still doing, the complexity is not going to be a barrier anymore. For example, Messi, MIMO, etc., need a very, very high complex signal processing techniques. So because of the silicon technology, people are still coming up with a new signal processing and coding techniques, which is very high complexity, but hoping this can be implemented in the future. And also the success of the 3G and 4G. 4G is the one first introduced OFDM, and 4G is the one first introduced multiple antenna technology as well. And 5G now we are talking about Messi MIMO with a large number of antennas. So all these, all these success story lead researchers around the world to do more research, because they see if they come up with a nice technology that can be implemented in 6G, so people are still, because of that motivation, people are doing more research. So because of these three reasons, more demand for connectivity, signal processing, complex signal processing, we can implement very nicely with a lower power signal processing technology. If you come up with a new technology like OFDM, MIMO, Messi MIMO, it is going to the standard and it is deployed. Because of all these reasons, people are still doing research on wireless communication. So wireless communication research is very, very active. Okay, now the AI and ML, how they can play a big role in the future wireless communication is a hot topic now. So compared to wireline communication, wireless communication differ wireline communication in two aspects. Okay, one is a phenomena called fading. Okay, one is the phenomena called fading. The other one is the phenomena called interference. Okay, so in the wireline communication, like a fiber optics or in the wired communication, there's no fadings. Okay, so the signal is going through the optical fiber or etc. The signal is not going to fade. But the wireless communication signal will go through the air, it will reflect, etc. At the receiver, it can add constructively or it can add destructively. The signal strength at the receiver will be fluctuated. So this is called phenomena called fading. So unlike the wired communication, wireless communication, the fading is one of the challenge that we need to mitigate or we need to exploit. Okay, the time variation of the channel strength due to small scale effect of multipath fading, as well as large scale effects such as path loss and shadowing, etc. The signal strength at the receiver will be fluctuating. This is called fading. The other one is called interference. Unlike in the wired world, where each transmitter-receiver pair can often be thought as an isolated point-to-point link, but wireless users communicate over the air, there's a significant interference between different user communication. So how to deal with fading and interference is the central design of wireless communication system. So this fading and interference are the big obstacle that we need to handle properly if we are wanted to design a good communication system. Okay, so the next this slide I'm showing you how interference is happening in the cellular network. So this figure is showing the uplink communication. Okay, so there is a base station here. The users are communicating to the base station uplink. So each user will send their information. Let's say they are using the same frequency and same time. So the base station will receive all the user information and they are interfere each other. So this is called a uplink communication. Uplink communication. There's another name called reverse channel. This is called reverse channel. So in wireless communication, there are three kind of societies are doing research. One is communication people, other one is called signal processing people, other one is called information theoretic people. The information theoretic people calls this channel as a multiple access channel or MAC channel. Okay, so this uplink channel have a three name: uplink, reverse channel, or multiple access channel. Okay, so you can see each user will send their information, they cause interference. So this is the interference, one of the interference scenario. So like here, the base station is sending information to the users. This is called downlink channel or forward channel. The information theoretic people call this is as a broadcast channel. So here also, base station send all the user information as a one waveform and send it through the channel, and each user will get their own message and also other user message as well, again cause interference. So these are the kind of scenarios for the interference. So this is another channel called interferent channel. So, in the cellular system for like Airtel or Vodafone, if they wanted to give a service to a particular area, what they do is they go and divide the areas as a hexagonal cell like this, and then put the base station at the center, and that base station will serve the user inside that cell. So this is the cells are normally designed like a hexagonal cell, and the base stations are they try to put at the center of the cell. Okay, so then if they wanted to use all the same frequency everywhere, because the frequency is very scarce resources, they pay a lot of money to government to buy these frequencies. They like to use all the frequency all the time, so and everywhere. Then if you use the that's called universal frequency reuse, then if the base station to one of the user here, the green link, that signal will cause interference to other cell users as well if they are using the same time, same frequency. So this is called a interferent channel. Okay, this is called an interferent channel. You can say this base station is communicating to this user. While doing communication, it will also interfere into other cell users as well. So this is called interferent scenario. Okay, so let's put this base station here, base station 1, this base station here, base station 2, base station here, base station 3. The user 1 is here, user 2 is here, and user 3 is here. And the green lines are the desired link, the red cross links are the interferent link. You can see this is called a multi-cell interferent channel. So this interference will affect the communication, because the channel capacity formula is 1 plus log 1 plus signal to interference plus noise ratio. If the interference is high, the interference plus noise ratio will be low, and the capacity will be reduced. So we need to handle this interference properly if we wanted to give a high data rate like a gigabits per second or terabits per second. So the handling interference and the fading is the big challenge in wireless communication. So I talk about fading. Next, I'm going to talk about I talk about the interference next. I'm going to talk about the fading. So there are two phenomena of fading. One is called large scale fading, other one is called small scale fading. Okay? So the large scale fading is due to path loss of the signal as a function of distance and shadowing by large object such as building and hill. This occurs as a mobile move through the distant order of cell size, and typically depends on frequency independent, or typically frequency independent. So the large scale fading is very important if you are designing the cell size and etc. Okay? And then other one is called small scale fading. This is the one the signal is traveled through different path, and at the receiver it can constructively add together, or it can destructively. So this is called small scale fading. Due to constructive and destructive interference of the multipass signal between the transmitter and receiver, this small scale fading occurring. This occur the spatial scale of order of carrier wavelength, and this is depends on the frequency. So this is the small scale fading depends on the carrier frequency. The FR1, FR2 that I mentioned. So the small scale depends on the carrier frequency. The large scale depends on independent of the carrier frequency. And this is for cell sites designing, and this is the one important for communication system design. Okay. So this diagram shows the wireless communication system is not an independent communication system. It is appendage to the wired network. Okay, so let's say so the cellular one cellular user wanted to communicate to some other user. So the first it connected to the base station. This link is not always the base station closer to the user will be connected. It's connected to the base station, have a very good signal to signal to interference plus noise ratio. So very good link. So the base user will connect it to the first base station. Then the base stations are connected through wired network. Okay, so the MTSO is one of the one of the center is called mobile telephone switching office. This is the one handling which base station need to be connected and which base station is handling the phone, etc. So this is the base stations are connected to MTSO, and then it will go to PT, public wired telephone network, and then it goes the phone call go to the destination. The destination may be the wired link like another home, or it can go to another cellular user as well. So what I'm trying to say is cellular network is not an independent network, but rather appendage to the wired network. Okay, this MTSO play a major role in coordinating which base station will handle the call to and from the user, and when to hand off the user from one base station to another. So I talk about this one already. So I'll skip this one. So objective of this fundamental wireless communication is given here. As I said, past 2 or 3 decades have been a surge of research activity in the field of wireless communication. Emerging from the research thrust, there are new point of view on how to communicate effectively over wireless channel. The goal of this course is to study in a unified way the fundamental as well as new research development. The concept are illustrated using example from several wireless standards starting from GSM to LTE and LTE Advanced and 5G new radio. So, in wireless communication, there are kind of 3 areas of the research that you need to understand properly. One is the channel model. So channel model mean from the base station to user, what's going on the channel model. Okay, so what's to model the channel, wireless channel. That is the wireless channels are different for FR1 frequency range 1. For millimeter wave is a different channel. Different channel for different frequencies and different bandwidth as well. So we need to model the channel as accurately as possible. Okay, so wireless channel modeling, maybe after lunch we will be studying those things as well. So once you model the channel, then you need to understand how much the capacity or data rate that channel can support. So this is the analysis called capacity analysis. Okay, this is kind of an information theoretic study. So once you know the channel model, how much capacity, or capacity means how much data rate that channel can support, okay, reliably. So capacity definition, there are 2 keywords: maximum rate that you can support reliably. So the maximum rate and reliability had to be there in the capacity definition. And then once you understand the capacity, this is the capacity, that's the channel capacity introduced by Channan. Once you understand the channel capacity, you need to to see how to realize that capacity, okay? What is the signal processing techniques, what is the coding techniques that we need to come up with to realize that capacity. So that is the second block of the research in wireless communication. Then the system implementation, okay? Then the system implementation. So if you are a wireless engineer, you need to understand all these three topic very well, okay? Channel modeling, the capacity analysis, and the communication techniques, what are the signal processing techniques, and we will study some signal processing techniques in this course, and then the system implementation. So the course outline, the basic course outline is going to be wireless channel. We will be studying some diversity techniques, multiplexers and interference management, capacity of the wireless channel, and part 2 is the modern wireless communication, which is including opportunity communication and multi-user diversity. MIMO, multiple input, multiple output, in this case, spatial multiplexing and channel modeling for MIMO, capacity analysis and multiplexing architecture, diversity and multiplexing trade-off. So these are very, very advanced topic. These are the topics that foundation for the LTE and 5G system, okay? So assumed background is the basic signal and system, linear algebra and probability, and basic digital communication course as well. So we are going to use this book for the next 2 days. This book is free. You can download this book from this website, Stanford University website. So the slides provide from this book. Okay, the slides are obtained from this book. So the book is available free. You can download. Okay, so any question? Okay, so the next topic is wireless channel. Maybe we can start after lunch. Maybe if you have a question, we can discuss. Sorry? Is Stanford, yeah. So he was at Berkeley before, and Pramit was his student. Yeah, so student. And oh, is it? Okay. Now he's in Princeton. Yeah. No, Illinois. He now moved to Princeton recently. Yeah. Yeah. So he, Pramit is a student of David Chai. So this book is, even though it's a bit old now, but this is still a classical book. You know, it's called Fundamental of Wireless Communication. It's not a fundamental at all. This is advanced wireless communication. Yeah, very deep book. So we will be hopefully we will be studying up to chapter 5, up to chapter 10 of this book, skipping a little bit here and there, but we will be focused on this book. Okay, I think we will take a small lunch break. And any question? Yeah. Advanced finance. Okay, so I need to go to other slide. Yeah. As I said, 5G is providing a three service, enhanced mobile broadband and massive message communication, ultra reliable low latency communication. 6G will be introduced 6 scenarios. The enhanced mobile broadband will become a new name. It's called immersive communication. The ultra reliable low latency got a new name called hyper reliable and low latency communication. And the massive message communication have a new name, massive communication. And apart from that 3 services, there are 3 services also introduced in 6G: integrated sensing and communication, AI and communication, and ubiquity connectivity. So answer to your question about the key performance indicators. So 5G, we are talking about 1 millisecond latency, but 6G we want 0.1 millisecond. Always we look for order of magnitude, so 10 order of magnitude, so latency, and the peak data rate, we want in 60 terabits per second. 5G will support gigabits per second data rate, so the reliability is, if I go further, yeah, so yeah, connection density. So in 10 million devices are connected in 1 kilometer per square. That is also another key performance indicator. Terabits per second, latency, and energy efficiency is 10 to 100 times better than the 5G. The spectral efficiency is further enhanced by 5 to 10 times. The spectral efficiency is already enhanced very much in 5G using massive MIMO technology. We expect to see even further enhancement. This is going to be ultra massive MIMO concept. Okay, so that's one thing. And position accuracy. Indoor we like to accurately localize 10 centimeter, but outdoor maybe 1 meter accuracy, etc. So these are the kind of a KPIs. Yeah. Yeah.
Third point in the previous slide.
Yeah.
Not this new parameters. So when we are going with the meaning of that endogenous network.
Yeah.
Yeah. What is the meaning of?
Okay, so it's like this machine learning will going to play a key role in the future wireless communication. What does that mean is the spectrum allocations and the resources allocation all are orchestrated by the machine learning techniques. So that's the dynamic spectrum allocation. Whenever the spectrum available, you can allocate very intelligently by using machine learning, and the resources allocation, the resources here also of a spectrum and energy, etc. as well. So, so AI is going to play a major role in the 6G to orchestrate the full wireless communication. So that's the one area AI is going to influence, and other area also people nowadays doing research on the receiver design for total transceiver design based on AI as well. So I don't know how successful that is going to be, but Nokia Bell Lab, even this GPU manufacturers are working on transceiver design using machine learning techniques. And the security and privacy are always the top priority for any wireless network as well.
The 5G, which is provided by India, Jio, other, is less than any country is developed millimeter.
Yeah, yeah, yeah. Yeah, yeah. China is doing for FR2 millimeter wave communication. They are the one maybe bit advanced on millimeter wave communication. But as I said, millimeter wave is not very successful. I mean, a lot of research have been done and very hype happened in the last decade. But you know, very few 5G traffics are 1 or 2% of 5G traffic is going through the millimeter wave. So having said that, people are now talking about terahertz. So I don't know how successful it is. So still FR1 is the good frequency to do research. Yeah. So, but very small cell indoor environment FR millimeter wave may be successful. Yes. Yeah, because of the path loss is the big issue. And the beam management, beam tracking, these are the issues.
CDAC has developed terahertz communication.
Sorry?
CDAC, this time the Indian mobile company,
Uh-huh.
CDAC has demonstrated terahertz based communication.
Okay, yeah. But what is the range? What is the range is going to be? Range? Yeah, yeah.
Within the
Oh, yeah, yeah. Range is going to be very small. It won't be.
terahertz are very high, but what is the application?
Application is yeah. Maybe one application is AR, augmented reality, etc. Between small areas, yeah. Our wearable will be connected through terahertz communication. Yeah, that's maybe the application. The data centers, the computers are connected with the ultra terahertz communication. That's also another application. But it's not going to be in the outdoor mobility environments. That is going to be FR1. Okay, I think we can take a lunch break and yeah. Welcome back. So I'm going to start wireless channel modeling. Okay. So here is the typical wireless environment here. So here is the transmitter here, sending signal to receiver here. This is the receiver here. Normally, there may be a direct path between the transmitter and receiver, or there may be a direct path and some reflected path as well. Okay. So this is the transmitter, and this is the receiver. The information is going direct path as well as some reflected path. So these two signal can add together constructively, or it can add together destructively. So the channel quality at the receiver varying in two fashion. One is in the solid line here. This is due to large scale fading, the solid line. The time constant is longer, and the faster fashion with the small scale fading. Okay, so the channel varies in a two spatial scale. One is called large scale fading. This is the large scale fading, the solid line, and the small scale fading. This is the small scale fading. So sometimes the signals are add together constructively. So this is here is add together constructively. Sometimes the signals are add together destructively. Okay, so this is the wireless multipath channel. So in free space, I'm going to talk about now the large scale fading and the small scale fading. Okay, in large scale fading in free space, receives power attenuate like 1 over r squared. R is the distance between the transmitter and receiver. Okay, so in free space, receive power attenuate like 1 over r squared. With the reflection and obstruction, can attenuate even more rapidly with the distance. detailed modeling is complicated. Okay, the time constant associated with the variations are very long as the mobile moves, many seconds or minutes. Okay, that's the time constraint. So this is the large scale fading. More important for cell site planning, less for communication design. So as I said, this large scale fading effect is this one, the solid line. This is more important for cell site planning rather than the communication system design. Okay. Now I'm going to move to small scale fading. The small scale multipath fading. Wireless communication typically happen at very high frequency. So this is the carrier frequency. We are talking about FR1, FR2 in the morning. So this is one of the typical carrier frequency in 3G, 900 megahertz or 1.9 gigahertz. So this typical frequency, multipath fading due to constructive and destructive interference of the transmitted waves. Channels vary when mobile move a distance of order of carrier wavelength. This is about 0.3 meter for 900 megahertz channel. So you know the formula F lambda is equal to C. C is the speed of light. So for 900 megahertz, the carrier wavelength is 0.3 meter. So if you are mobile or you move 0.3 meter, then the channels varies dramatically. So even if 0.3 meter, your channel quality is changing. So here the small scale fading depends on the carrier frequency. For vehicle speed, this translates to channel vehicle speed. For the vehicle speed, this translates to channel variation of the order of 100 hertz. So I'll come back to you in a minute. How do you get this 100 hertz in a minute? Okay. Primary driver behind wireless communication system design. So the small scale multipath fading is primary driver behind the wireless communication system design. So the game plan is we wish to understand how the physical parameters such as the carrier frequency and the mobile speed, the bandwidth, the delay spread, the angular spread, etc. Impact the wireless channel behavior from communication system point of view. So we wanted to understand how these parameters, carrier frequency, mobile speed, and the bandwidth, delay spread. I will define what is delay spread in a minute. Angular spread, etc. Impact the wireless channel behavior, and that's lead to communication system design as well. So that's the plan. Okay. So the plan is to we start with a deterministic channel model from transmitter to receiver. We try to do a deterministic channel model. At the end, we will say the deterministic channel model is not the appropriate way to do it. We need a statistical channel model. So that's the story that I'm going to tell you now. Okay, we start with the deterministic physical model and progress towards statistical model. The statistical model is the one you may heard about, relay fading, Ricean fading channel, Nakagami fading channel. These are statistical models. So we start to model physically deterministic model. At the end, we say, you know what, deterministic model is not the good way to go. We need a statistical model. So that's the story. So which are more usual to design performance evaluation. So statistical models are good to have the performance analysis. If you design a communication system and you assume the channel is a relay fading channel, then you can analyze the performance bit rate curve or capacity, etc. Easily rather than the deterministic channel model. So physical channel model, so let's start with the physical channel model. So the wireless channels can be modeled as a linear time varying system. So as I said, there is a transmitter here, let's say TX, and there's a receiver here, let's say RX. There will be a reflected path going. The channel have a attenuation AIT, and the delay to IT for this path. Okay, there's another path going as well. It have a different channel attenuation and delay as well. So there are many paths are going from transmitter to receiver. So the channel model, the receive signal here. So this is the transmitted signal, let's say XT, and the receive signal, let's say YT. The YT can be modeled as a summation of many paths. Each path have its attenuation coefficient AIT, which is a time dependent parameter, and the delay to IT. So the summation of all the paths at the receiver will give you the receive signal. Okay, so the where AIT and the to IT are the gain and the delay of the each path. Okay. The time varying impulse response, okay, so let's say if you put a signal here, you will get the receive signal here, but if you put an impulse here, you will get the impulse response. So if the receive signal become impulse, then you will get a impulse response. So time varying impulse response can be modeled by this equation here. The only difference is instead of transmitted signal, you are putting impulse here, you will get the impulse response. Okay? So now first, as a special case, we consider time invariant channel. So let's say the channel is time invariant. So this is the depends on T is not there. So only delay, which is not time dependent. The attenuation, which is also not time dependent. So this is called time invariant channel impulse response here. Okay, so this is the diagram is showing the pass band to base band conversion. So you know, so the pass band spectrum looks like this. Okay, the pass band spectrum looks like this. This is the carrier frequency FC, and this is the bandwidth W, and this is this point is FC carrier frequency plus W over 2, and this point is carrier frequency minus W over 2, and you have a same spectrum here. So this is the spectrum of pass band, and the spectrum of base band looks like this. Okay, so this is the bandwidth. So if you have a larger bandwidth, okay, larger bandwidth, then you can send more data. So it's like you consider this as a tap. Okay, if you have a bigger tap, you can get a more water. Similarly, if you have a larger bandwidth, you can send more data through this channel. Okay, so this is the bandwidth. Okay, bandwidth is this one. Okay. So communication takes place FC minus W over 2, this guy, FC plus W over 2, this is the bandwidth. Processing takes place baseband. So the process, everything that we do a baseband signal processing. So this is W over 2, and this is the minus W over 2. All the this is a baseband signal, this is the baseband signal, and this is the passband. Okay, passband signal. So all the signal processing happening at the baseband, but the communication happening at the passband. That's what it's saying there. Communication takes place at FC minus W over 2, FC plus W over 2. If we have a larger bandwidth, okay, so in 5G we have a bandwidth like a 5 megahertz channel, 10 megahertz channel, 20 megahertz channel. If we do a carrier aggregation, we can go up to 100 megahertz channel, okay? And if you are talking about millimeter wave, you can go up to 400 megahertz channel as well, okay? So those are bandwidth. So bandwidth, if you have larger bandwidth, you can get more data rate, okay? Anyway, so processing takes place in the baseband. Okay, so this is the kind of a communication block diagram. So you have a signal, in-phase component and the quadrangle phase component. If you multiply by cos and the sine here, what you are doing is you are up-converting the baseband signal to passband signal. So at the transmitter, your mobile phone at the transmitter, you do the last step, up-convert your baseband signal to passband signal and transmit through the channel. So the up-conversion is mean you multiply by cos and the sine in phase component and quadrangle phase component, multiply by this sine and cos mean you are converting to signal to the passband. And that's the first, last step that you at the transmitter, and you transmit that signal xt through the antenna. At the receiver, it will go through the communication channel. At the receiver, the first step you do is to down convert the signal. The down conversion also multiply by cos and sine. So you down convert the signal to baseband signal and do the processing at the baseband. Okay? So this is the diagram explaining this part is the up converting the signal to carrier frequency and transmit it through the channel. At the first step, at the receiver, you down convert the signal and do a low pass filtering and get the baseband signal, and all the signal processing happening at the baseband. Okay, so so baseband, complex baseband equivalent channel. The frequency responses, response of the system is shifted from the passband to baseband, from the passband to baseband. So the HBF is denoted by this. This is in frequency domain channel, and in time domain channel, you can write it like this. Okay, so you can see the channel is have a many paths, have a gain and the delay. So each path is associated with the delay and the complex gain. So, so here, this diagram is showing, you have a digital signal here. There are two additional blocks here. There is a digital signal here, and you go through this sync function, and you get the continuous signal here, and then similar thing, up conversion, and then down conversion, and filtering, and sampling, and you get the digital signal here. So this is the digital signal and the discrete signal here, discrete signal here. So only different is, this sampling and discrete signal go through this sync function. So now the multipath resolution. So sample baseband equivalent channel model. So the received signal now can be written as, so you have a transmitter here, Tx, and you have a receiver here, Rx. You send many paths are coming here. Your received signal can be written as Ym is equal to summation of HL. This is the channel coefficient, and then the transmitted signal M minus L. So this is the, so many paths are add together. So this is the receive signal model in the discrete model, okay, sample baseband equivalent channel, okay. So this HL, this guy, this is the channel coefficient, where HL is the Lth complex channel tap, can be modeled by this way. And the sum is over all paths that fall into delay bin this. So what is this one is saying is, okay, so you have a delay bin. This is, L over W plus 1 over 2W. And this is L over W minus 1 over 2W. So this is the 1 over W. So this is sampling duration, TS, okay? This is the sampling duration. During this sampling duration, there are many, many paths are coming here. Lot of paths are coming here. All these energy are denoted by HL, okay? So this is the channel coefficient, HL. During this delay bin, there are many, many paths are coming, and all this energy together, you denote as a channel coefficient. So that's the one denoted by HL, okay? HL is the Lth complex channel tap and denoted by here, and the sum is over all paths that fall in the delay bin, this one, okay? So if you have a larger bandwidth, this delay bin is very, very small, 1 over W is small, so you can resolve very finer. But if you have a smaller bandwidth, this guy is larger, so you won't be able to resolve very finer. So bandwidth is very important parameter, okay? So system resolve multipath up to a delay of 1 over W. 1 over W is the sampling duration. So here is the example here. So you can see this is the I is equal to 0 path. I show you here. There are many paths coming. There are many paths coming here. Okay. So if you go here, so I is equal to 0. I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4. This is the L here. So this one is H0. This is the channel coefficient for H0, okay? And the next one is channel coefficient for H1. And next one is the channel coefficient for H2. So what is this diagram is showing is this delay bin, the contribution of the main path from I is equal to 0 and I is equal to 1. So those are the main contribution to this channel coefficient. Okay, so the next H1, the main contributions are from L is equal to I is equal to 2. So this is L is equal to 1. Okay, the last channel coefficient H2, the main contributions are L is equal to I is equal to 3 and I is equal to 4. So this is the kind of a showing that each channel coefficient, which of the path contributing to the major energy. Okay, so HL is the Lth sample of the low pass version of the channel coefficient. Contribute to the ith path of is the projection of this is that. Okay, so anyway, so what I'm saying is, so these are the channel gain, and which path are contributing to that channel gain. Okay, so now I'm going to show you some definitions. So these are very important definitions. The channel can be modeled as a flat fading channel or frequency selective channel. Okay, so these are the two models that we have. One is called fading occur when there is a destructive interference of multipath that contribute to the tap. Okay, so the first definition is called delay spread. So delay spread mean, so you have one path coming from the transmitter to receiver very quickly, let's say Ti min. There's one path very far away, going far away and reflected in many, many places. I'm coming to the receiver very low after long time. So the long time minus short time is called delay spread. Okay, so that is called delay spread. So definition of delay spread is max ij, this one. Okay, so the maximum delay minus minimum delay is going to give you a parameter called delay spread. Okay, and 1 over delay spread is called coherent bandwidth. Okay, 1 over delay spread is called coherent bandwidth. Okay, so if the delay spread is less than the bandwidth, so the bandwidth is very important, okay? If the delay spread is less than the bandwidth, okay, or the coherent bandwidth is greater than the bandwidth, then we can use only a single tap, and so the received signal ym can be modeled as a h plus xm, okay? So we can model like this. So this is called a flat fading channel, okay? This is called a flat fading channel. To have a flat fading channel, we should have a coherent bandwidth is larger than the bandwidth of the communication, okay? If the coherent bandwidth is larger than the bandwidth, so the coherent bandwidth is 1 over delay spread, okay? So then single tap flat fading channel. If the coherent bandwidth is less than the bandwidth is larger, then we have a frequency selected channel. So this is the frequency selected channel. So we need a multiple tap, okay? We need a multiple tap. So this is a flat fading channel, okay? And this is a frequency selected channel. So these are the two channel model that we used in the communications, okay? So if we have a frequency selected channel, then we can use OFDM technology to make it a frequency selected channel to a flat fading channel. So we will see that later on. So any question? So the delay spread is very important. It's a maximum delay minus minimum delay is give you a delay spread. 1 over delay spread is called coherent bandwidth. If the coherent bandwidth is larger than the bandwidth, we say flat fading channel. If the coherent bandwidth is smaller than the bandwidth, we say frequency selected channel. In the frequency selected channel, we need a multiple taps. Frequency selected channel, we need a multiple taps, okay? So these are the very important channel model, okay, flat and frequency selective fading. So in this diagram is showing a same channel from the transmitter to receiver, same physical channel, but we are seeing the channel in a different frequency, okay, different frequency. The same channel, this is in time domain, this is in frequency domain, but we have a different bandwidth. So here the bandwidth is 200 megahertz channel, here the bandwidth is 400 megahertz channel. So here the bandwidth is larger compared to here, and you can see here the bandwidth is larger, so the duration, the sampling duration is smaller, so you can resolve the path very finer, and you will have a multiple taps. So you will have a multiple taps, so this channel become a frequency selected channel. Or in other words, in this case, the bandwidth is larger than the coherent bandwidth, so we need a frequency selected channel. So in this case, you need to model the received signal like this frequency selected channel, because you have a larger bandwidth. Larger bandwidth means smaller duration, sampling duration. So you resolve the multipath very finer. So you will get many channel types. So you need a frequency selective channel model. But in this case, but both are same channel, receiver, transmitter, they are in the same places, okay? But bandwidth of the communication is different, okay? Here, the bandwidth is smaller, okay? The bandwidth is 40, here is 200 here. So the sampling duration is longer, and you cannot resolve very finer. And in this case, this channel is modeled as a kind of a flat fading channel, okay? So it's saying effective channel depends on both physical environment and bandwidth, okay? So the bandwidth of the communication, I told you about the bandwidth, is very important. If you have a larger bandwidth, you will end up having a frequency selected channel. And in frequency selected channel, the receiver complexity is high as well, but we can use OFDM, etc., to reduce the complexity. Anyway, so So the important message here is, the physical channel is going to be same, but the communication bandwidth is different, then the channel model, the way you model the receive signal is going to be different. If you have a larger bandwidth, the sampling duration is smaller, you will resolve the signal very finer, and you will end up having multiple taps. So next definition is Doppler shift. Okay, so the receive signal, this is the frequency selective channel. Okay, you can see there are many path taps are here. This is the frequency selective channel. And this parameter, FC, carrier frequency into delay, is called Doppler shift. It's called Doppler shift. The carrier frequency into delay is called Doppler shift of the ith path. And the Doppler spread is defined by this definition here. Maximum Doppler shift over minus minimum shift will give you a Doppler spread. So 1 over Doppler spread is called coherent time. Coherent time is the time the channel is constant. Okay, coherent time is the channel is constant. So in the communication, every coherent time your mobile estimate the channel. So channel will be random and constant during the coherent time, and taking another random realization and constant for another coherent time, and then taking another random realization and constant for the coherent time. So the coherent time is 1 over delay spread. Okay, coherent time is 1 over delay spread. Okay, so this is the, I told you that 100 hertz Doppler spread. I'll come back to that later. So this is the kind of a, so here there's a transmitter antenna here, and there's a wall here, and this is the receiver. There's a car, you can think of as a car moving in a speed of v. So there's a direct path, okay? There's a direct path, and there's a reflected path as well. So this direct path have a Doppler shift of 50 hertz, and the reflected path also have a Doppler shift plus 50. So the delay spread, Doppler spread is 100 hertz. So you can, put the equation. So this is FC over V over C. You will get that Doppler spread. Okay. Yeah, so for example, so here FC is 900 megahertz, 900 megahertz into V is 60 into 10 to the power 3 over 360 over C 3 into 10 to the power 8. You will get this one is 50. Okay, so this is the way you calculate the Doppler shift. Okay. So the Doppler shift is FC into tau, that is this, and this is going to be, okay, so the direct path have a Doppler shift of minus 50, and the reflected path have a Doppler shift of plus 50, and so the Doppler spread for this guy is going to be 100 hertz. That's what I said, how do we get this 100? I will come back to you later. This is the calculation. So, so the Doppler spread is given by this expression, okay? Doppler spread is proportional to carrier frequency. Of course, if you have a larger carrier frequency, your Doppler spread is higher. Angular spread of the arrival path is given by this V over C cos theta I. In the previous, the theta is the angle of the direction of the motion make the ith path. So in the previous here, the theta is 0, and here the theta is 180. That's why this is minus and this become a plus as well. So Doppler spread is another important parameter. So 1 over Doppler spread is a coherent time. Coherent time is the time the channel is constant. So every coherent time, your base station estimate your channel, And similarly, every coherent time, your mobile phone also estimate the channel, and then during that coherent time, portion of the time is used for channel estimation, another portion of the time is used for data communication, okay? So channel estimation is happening everywhere, every coherent time. So the coherent time are normally, larger in the millisecond range. So here is the typical parameter. I'm showing here some parameters, not to exactly try to see the numbers. What you have to see is what is the kind of a order, okay? So for example, what you have to remember is carrier frequency in wireless communication in the range of gigahertz. That's what you need to know. It's not 1 gigahertz. You need to know the carrier frequency typically in a gigahertz range. Your Wi-Fi is 2.4 gigahertz, and similarly for 5G communication in a gigahertz range. FR1 is going out to 7.125 gigahertz. The bandwidth, another one is in the megahertz range. So we like to see feeling of, but if we talk about bandwidth, we need to see the feeling that is in the range of megahertz. Distance between transmitter and receiver, if we are talking about microcell in the highway and all these areas, it's like a kilometer radius. Velocity of the vehicle is at 64 kilometer per hour. So the direct path is 50 kilohertz, 50 hertz Doppler, and the Doppler spread is 100 hertz. So time scale changing of path is 1 minute here. Time scale change of phase is 5 milliseconds, etc. So here, these are the kind of a coherent time is 2.5 milliseconds. So if we are talking about coherent time, you should have a feeling is in the millisecond. So every millisecond range, you need to estimate the channel. So that's the one. Delay spread in a microsecond. Okay, so you don't need to remember 2.5, but you need to remember delay spreads are in the microsecond. Okay, coherent bandwidth is 500 kilohertz. So you need to know the coherent bandwidth in the typical wireless communication is in the kilohertz range. So that's why this slide is shown here to get the feeling what is the kind of order of magnitude. So there are some more definition here. Fast fading channel, slow fading channel, flat fading, frequency selective, underspread, etc. So if the coherent time is the time the channel is constant, is very, very less compared to delay requirement. Delay requirement of the service is another thing. So if you are talking over the phone, your delay requirement is like in 100 milliseconds. If you are talking to somebody, the delay requirement is in the 100 millisecond range. So if you are downloading videos or files, your delay requirement may be larger than that, okay? So it's all relatively. So if the coherent time, okay, very, very less compared to delay requirement, we say the channel is fast fading channel, okay? Which is all relatively what application is, okay? If the coherent time is the time channel is constant, is very, very small compared to delay requirement, then you say the channel is fast fading channel, okay? If the delay requirement, coherent time is very, very large compared to delay requirement, then you say slow fading channel, okay? If the bandwidth is very, very small compared to coherent bandwidth, you say flat fading channel. If the frequency selective channel, now bandwidth is very, very large compared to coherent bandwidth, you say frequency selective fading channel. If the delay spread is very, very small compared to coherent coherent time, then you say underspread channel. So there are many, many parameters and definition for the channels, typical. The wireless channel is very important. You need to understand wireless channel properly to understand the wireless channel is important to find the capacity analysis and the communication system design, etc. So different channel have a different design. Okay, if you have a frequency selected channel, you need to use OFDM technique. Okay, if it is a flat fading channel, you can use TDMA, etc. So it's a different channel have a different receiver design. Okay, coherent time, typical channels are underspread. Coherent time depends on the carrier frequency and the vehicle speed of order of millisecond or more. So coherent time is the, you need to understand coherent time is in the millisecond. Okay, every millisecond you will be estimating the channel, your phone is estimating the channel between you and the base station. Okay, so the estimation is happening in the order, every millisecond. Okay. The delay spread depends on the distance to the scatterer of the order of nanosecond in the indoor environment. So in this indoor environment, the delay spread is in nanosecond. If it is outdoor environment, is in the microsecond. Okay. Channel can be considered as a time invariant over long time scale. Okay. Channel is considered as a time invariant channel for the long time scale. So, so as I said, we modeled the channel so far by using physical scattering, attenuation and delay, etc. But in practice, when you do performance analysis of your communication system and simulation, etc., we don't do a channel like this. We assume a statistical channel model. Okay, so statistical channel model, design and performance analysis based on the statistical ensembler of the channel rather than specific physical channel. So the channel here coefficient, each of the channel coefficient is written as this form here, and then this guy can be modeled as this random variable. Okay, so if it is so you have a channel HL is modeled as a complex. These are complex channel X plus, let's say, JY, and X comma Y, they are distributed as normal, zero mean, half variant. Okay, X and Y are distributed as zero mean, variant, half, and then this guy is distributed as complex normal, zero mean, variant 1. Okay, so these are the statistics. I hope you may seen this one. This is the complex number X comma JY. This real and imaginary part are distributed as normal, real. Okay, normal, zero mean, variant, half, and then we say this guy is distributed as complex normal, zero mean, variant 1, and then this guy squared is distributed as exponential distribution with the parameter 1, okay, and this guy distributed as, this is the magnitude squared, this is the magnitude, this is distributed as Rayleigh. Okay, so this all you should know. So if you are doing some exam question, the exam paper saying your channel is distributed as complex normal, then you should know immediately that magnitude squared is an exponential distribution, the magnitude is a Rayleigh distribution. Okay, so this Rayleigh distribution is one of the popular model in the wireless communication. So Rayleigh flat fading channel, many small scatterer path, the channel is, real part is normal half variant plus imaginary part zero mean half variant. So in this case, we say it's a complex normal zero mean variant 1, and this is called circularly, a complex circularly symmetric Gaussian channel, because if you multiply, rotate this distribution, this complex number, the statistics won't change. So that's why it's called complex circularly symmetric Gaussian random variable. Okay, what is circularly symmetric complex random variable? HL and HL e to the power j pi, they both have the same distribution. So that's why it's called circularly symmetric. So if you do circularly symmetric, multiply by some, rotate the signal, rotate the channel coefficient, your distribution is not going to change. That's called a complex circularly symmetric Gaussian random variable. Okay. So relay distribution channel, so channel coefficient. So your channel coefficient is now modeled as a statistical model. Okay, we use a statistical model. We are not going to model the channel between transmitter and receiver by how many paths are going, each path gain and delay, etc. We put all these paths together. We say is a relay distribution or complex normal distribution. Complex normal is this, and its magnitude is relay, and magnitude square is exponential. Okay, so this relay distribution is used. You have a transmit antenna, you have receive antenna. So you only have a scattered, reflected path. There's no direct path. There's no direct path. Then you model the channel as a relay distribution. Okay, but if you have a direct path always exist between transmitter and receiver, then you need to go with a different model. It's called Ricean model. Okay, line of sight plus scattered path. These are called scattered path. There's no line of sight. You model as a relay distribution. If there is a line of sight, then you model as a Ricean distribution. You can see Ricean distribution have a non-zero mean. Here, zero mean, and Ricean zero mean because there's no direct path. And if you have a scattered path plus the direct path, you have a mean here. So in that case, we model the channel between transmitter and receiver as a Ricean model. So these are the two important models we use in wireless communication. There are some other models like a Nakagami fading channel, etc. as well. So next one is correlation over the time. So this is the channel coefficients are correlated. Okay. So there is a famous model called Jake's model. So what is this saying is that the transmitter is fixed. Okay, transmitter is fixed. The receiver is moving. But the receiver is surrounded by many scatterer, and the channel coefficients are time varying. Okay, varying. Then the channel time variation is modeled as a correlation here, channel correlation, autocorrelation, and the power spectrum is given here. Okay, specified by autocorrelation. So correlation over time is specified by autocorrelation function and power spectral density. So this is the special case is called Jake's model. Transmitter is fixed, but the receiver is moving. The surrounding of the receiver is having many scatterers. Okay, then the time variation is modeled as an autocorrelation function here, and its power spectral density is given here. Okay, so in our communication system, there is always the noise presence in the receiver, thermal noise, etc. So the receive signal, this is the frequency selective channel model. The receive signal always added with some noise as well. So complex baseband equivalent channel model. So this is the frequency selective channel model because there are many types here. Okay, the receive signal at time m is given by this expression here. This is the noise. Okay, noise is also we model as a complex normal, zero mean, variant in node. Okay, and this is the frequency selective channel. If the tap, there's only one tap, there's no summation here, we call flat fading channel. So this is the flat fading case. Okay, so these are the channel model that we use for our communication system design. Okay, so this guy is a relay fading. Its magnitude is relay fading. Its magnitude square is exponential distribution, etc. You should know immediately. So we will be using this model throughout the course. Any question? Okay, so any question, please ask me. Summary. So we have understood how the time and frequency selective wireless channel depends on key physical parameters. Key physical parameters are bandwidth, the carrier frequency, and etc. Okay, we have come up with a statistical model, channel model that are usual for analysis and design. Okay, so I'm going to show you some more summary. So we start with the large scale fading. So the variation of the signal strength over distance of order of cell size, receive power decrease with distance r. This is the attenuation. This is 1 over r squared. If the r, transmitter, receiver are very, very far, your signal is attenuated. The attenuation is 1 over r squared in a free space, 1 over r to the power 4 reflection from the ground plane, etc. Decay can be even faster due to shadowing. Shadowing means your transmitter receiver, there is a building or tree blocking the signal. It's called shadowing, etc. If you have a shadowing, a decay can be even faster due to shadowing and scattering effect. And then we study small scale fading. The variation of the signal strength over distance of order of carrier wavelength. So the carrier wavelength we saw 0.3 meter in the 900 megahertz channel. So if I move 0.3 meter, my channel will change. Okay, so that's what is saying. Okay, wavelength due to constructive and destructive of multipath. The key parameters are the delay spread. Okay, delay spread, 1 over delay spread is the coherent time. Coherent time is the time the channel is constant. So channel is random, but each coherent time, each coherent time, it will take a random realization and stay constant, and take another random realization, take constant, etc. That's the way the channel behave. Okay. Delay spread is proportional to velocity of the mobile and to the angle spread of the arrival path. So 1 over delay spread is called coherent bandwidth. Okay? Delay spread is proportional to the difference between the length of the shortest and longest path. So this is the kind of a discrete time baseband signal for the frequency selective channel. The Lth path, the channel Lth path, is a summation of many, many paths aggregated through this delay pin. Okay, so that is also another thing. In that one delay bin, there are many, many paths are coming, independent paths are coming in that 1 over W sampling duration Ts. There are many, many paths are independent paths are coming. So we add together, we model that channel as a complex normal. Okay, so this is kind of a law of large number. Statistics also kick into this theory as well. Many, many independent paths add together, we can model as a Gaussian random variable. Okay, so this is the relay fading channel model, and this is the Ricean fading channel model. Okay, so I think that's all I would like to say about the channel. Do you have any question?
Why do you always consider only AWGN channel as most of the times?
Okay, so AWGN channel is the non-fading channel. Okay, so so when you study digital communication in your undergraduate classes, you model the receive signal y is equal to x plus w noise. Okay, so this is the AWGN channel. AWGN mean additive white Gaussian noise channel. There is no fading. There's no fading. Nothing here. But when you study wireless communication, you introduce wireless communication, we have a fading, okay? So we have a receive signal now is modeled as Hx plus W. This guy is the fading. This is due to fading, and this guy is distributed as complex normal, 0, mean, and 1, as I said, and this magnitude is Rayleigh fading, okay? So this is the AWGN channel, there's no fading, and this is a fading channel. This is the flat fading channel. Okay, so this guy is a random variable. So this guy is the one going to cause a lot of problem, okay? Because AWGN channel, your bit error rate curve, I will show you tomorrow. This is the probability of error versus SNR is decreased exponentially, okay, for the AWGN channel. But for the fading channel, this is not decreasing exponentially, it is going 1 over SNR. So because of this, the performance of fading channel is very bad. We need to do extra thing, clever design. We can introduce diversity, etc. So that's we will be looking at tomorrow's class. Any other question on AWGN channel? Yeah.
And we are taking complex circularly symmetric Gaussian.
Yeah, random variable. Yeah, the fading coefficients are complex circularly symmetric Gaussian random variable.
Okay.
0 mean, variant band.
Since we are saying symmetric, we are considering like a Gaussian.
Yeah.
Gaussian.
Gaussian model. Yeah. Model. Yeah. It's complex 0 mean, variant 1, and its magnitude is the one Rayleigh fading. Okay, so we can say its channel is complex normal 0 mean. Then immediately its magnitude is Rayleigh and magnitude square is exponential. All these things immediately you should remember. All these things are needed to analyze the performance. If you wanted to design a system and say what is the diversity order, what is the etc. To calculate all these things, you need all these statistics. Okay. Yeah. Any other question? Yeah, I think wireless communication is a lot of mathematics involved. So this is kind of a simple methods. So if you have a MIMO channel, then we have a transmitter receiver. It's going to be not just a scalar, it's a matrix channel. So things are very, very complicated. We will see that MIMO channel on Wednesday morning, etc. Any other question? Do you know all these things before? Okay. Anybody knows all these things before? Okay. You know. Okay.
Not completely, sir, to some extent.
Oh, okay. Thanks. Any other question?
We do have many types of statistical models.
Uh-huh.
Like we have discussed Rayleigh and the ratio.
Yeah.
We even have Nakagami and other types of.
Oh, yeah.
So among these models, which will be the appropriate one?
Normally, Rayleigh fading is good enough. Rayleigh fading is the if you are doing some performance analysis, etc. Rayleigh fading is easy to deal with analyzing. Because of this mean guy, Ricean fading channels are very difficult to analyze. Very difficult. They get a closed form solutions, etc. is very difficult. For Rayleigh fading, there's no mean. Mean is 0. Things are easy. Performance analysis is easy. But if you are talking about, yeah. Nakagami also very little bit more complex as well to analyze, doing performance analysis.
All scenarios.
Huh?
Not all scenarios.
Uh-huh. Yeah. It depends on the scenarios. Okay, the normal models is Rayleigh model is the normal channel model. Yeah, but people start modeling assuming this channel I'm doing as a Nagami fading and deriving the performance analysis. You know, for the publication purpose, people do all these kind of things as well. But you know, in the David Shai's book, always use relay fading. Any other question? Maybe we can have a break then. Okay. Yeah. Yeah, yeah. So. Yeah. Sorry? Okay, okay, yeah. Yeah, yeah. So that's why, yeah, you can call, but if you want any discussion, we can discuss. Sorry? Uh-huh. I think for research, you know, for the so whatever we studied here is kind of a single input, single output case or CISO model. I think the all the performance analysis, etc., for single input, single output system are well studied. So there's not much to do now. Okay, but probably tomorrow and day after tomorrow, we will see different like a single input, multiple output case, or multiple input, single output, or MIMO, multiple input,